So this is the last video dealing with Hess's law, and in this video we're going to look at this concept of bond dissociation energy, which, as you can see here, is defined as the average enthalpy change needed to break 1 mole of a particular bond into 1 mole of gaseous atoms. And you will very often see this shortened to bond energy. So bond dissociation energy, bond energy, same thing. So straight into a high text alert. Let's look at try to tease out this concept a little bit. So if we have this molecule XY, this molecule XY might look something like this: X with a bond to Y. And so if we're going to break that bond, we will yield 1 mole of X, there it is, and 1 mole of Y, there it is. So you don't have to worry in this case about what X and Y are. Doesn't mean they're ions or polyatomic ions. You just break everything down into the constituent atoms that were associated with a particular bond. Bond dissociation energies obviously give a bit of indication about stability of a molecule, and we can look at a couple of simple diatomics. Hydrogen. So hydrogen gas yields 2 hydrogen atoms, or 2 moles of hydrogen atoms. The bond dissociation energy is positive 432 kilojoules. Oxygen, on the other hand, yields 2 moles of oxygen atoms with a higher bond dissociation energy. Any idea why that bond dissociation energy is higher? Well, look at the bonding. Hydrogen, H single bond H versus oxygen, O double bond O. So it's that double bond that's going to give rise to a higher bond dissociation energy. And you'll see that in a minute with other types of bonds. All right. Now, let's look at a scenario just to start realizing how are you going to tackle these problems. So if we have our balanced chemical equation for the complete combustion of methane, there it is. Methane plus 2 moles of oxygen yield carbon dioxide plus 2 moles of water. Well, let's first of all consider the reactants. How many bonds do you see? What type of bonds do you see? So this is where you might want to draw what are known as stick diagrams. Stick diagrams are much more like Lewis diagrams, but bonds only. So in our reactants we have methane. There it is, CH4. There's a stick diagram for methane. That's actually also a Lewis structure for methane. And we have oxygen, 2 moles of it, and oxygen looks like this. And so again, here's you can kind of see it again. So there's a methane molecule. So there's my carbon hydrogen bond. Oh, there's another carbon, so 4 carbon hydrogen bonds. There's my oxygen with the O double bond O. And so what I actually have then is, in terms of bonds, I have 4 times my carbon hydrogen bond, right? 1, 2, 3, 4. I have to break all of those bonds. And I have 2 times my oxygen double bond because I have 2 moles of it. All right. Now, bond breaking obviously is endothermic. I can kind of demonstrate that. Here's my methane again. I'm going to break this carbon hydrogen bond. Oh, okay. So that obviously took some energy. So endothermic process. Now let's look at the products. So again, a stick diagram here would be useful. Carbon dioxide. Well, there's the molecule of carbon dioxide. So hopefully, again, you will see and come to realize the type of bonding involved there. So, and there's water. So again, my water molecule, I have a hydrogen oxygen bond, but I have 2 of them in water. And so in terms of a stick diagram, doesn't hurt to rattle one of these off. So carbon dioxide, 2 double bonds. Carbon oxygen double bonds. And my water, I have 2 moles of it, and that's that. So in terms of bonds, I have 2 times C double bond O, 1, 2 in the one molecule, and I have 4 times O bond H because I have 2 moles of 2 bonds. So it is important when you look at bond dissociation energy that you have a very good understanding of the type of bonding, C double bond O, and number of bonds, 2 times C double bond O, or 4 times O bond H. And the process of bond formation is, by extension, exothermic. I can't really show that with molecule because it actually would be endothermic. I'd be applying energy to add those bonds. But if bond breaking is endothermic, bond formation is exothermic. All right, so this brings us to this interesting equation. So this is another one you need to know. And basically, it's pretty straightforward. Enthalpy of reaction equals sigma n bonds broken minus sigma n bonds formed. And you should remember from the previous equation with Hess's law, sigma is sum of. So the sum of all the bonds that are broken. N is the molar ratio of those bonds. So that's why when we have 2 moles of C double bond O, bond double bond O, what we actually have would be 4 times carbon oxygen double bond. Okay, so that's what the N means, and so that's what I said is you really have to have a good appreciation of that side of things. Now, bond energies come from tables, just like bond standard enthalpies of formation. So here's a very common one: carbon hydrogen single bond. Oxygen hydrogen single bond is another one you encounter a lot. Oxygen oxygen double bond, when it's oxygen, the molecule. C double bond O. But here's the one you probably see more when it's C double bond O. C double bond O in CO2 is actually a more stable bond than a C double bond O in some other molecule, like an aldehyde or a ketone. So you do have to be aware of that. And then we have all these different multiple bonds for different, usually they come up in the organic side of things. Anyways, let's start applying this process. Okay, so back to our reaction. Let's get our quick stick diagram out there. And so there's our methane plus 2 moles of oxygen yields 1 mole of carbon dioxide plus 2 moles of water. And so now we can use our equation and start doing our calculations. And so it's always bonds broken minus bonds formed. So we now start on the left hand side. So we have 4 times carbon hydrogen bonds plus 2 times oxygen double bond. So there's our bonds broken minus the bonds formed. We have 2 times carbon double bond O plus 4 times oxygen hydrogen single bond. And that's our bonds formed. And so again, we would do the math on this one by starting with the substitution. So again, looking at our table of bond energies, we see that a carbon-hydrogen bond is 413 kilojoules. So it's going to be 4 times 413. Whoops, let's try that one again. 4 times 413 kilojoules plus 2 times oxygen double bond has a bond energy of 495 kilojoules minus 2 times carbon oxygen double bond in CO2 is 799, and 4 times our OH bond, which has a bond energy of 497 kilojoules. And then we just carefully number crunch. And so what we get here is 2642 kilojoules associated with bond breaking minus 3,586 kilojoules associated with bond formation. And so when we subtract, we get negative 944 kilojoules. So exothermic, which we would expect for a combustion reaction, combustion of methane. And so you can see how all bond energies are always positive, but this negative in the middle, so bonds broken minus bonds formed, this is what's going to give rise to a negative delta H of reaction. If the energy associated with bond reformation is larger, you get an exothermic reaction. Let's look at another one. So this is the combustion of ethanol. And so again, we would expect this to be exothermic, and it is likely going to be exothermic. And so again, a simple stick diagram to begin with. And so there's the stick diagram for ethanol. 3 moles of, again, oxygen, double bond oxygen. 2 moles of CO2 and 3 moles of H2O. So there's the stick diagram. So that allows us to start counting bonds. And so there's another way you can approach this. We can just look at this as bonds broken. Let's treat this by itself to begin with. Bonds broken. And so bonds broken is going to be 1 times the carbon-carbon single bond. That's this bond right here. So there's only one of those. And so that has an enthalpy of, bond enthalpy of 347 kilojoules. And I have 5 carbon-hydrogen bonds, each with a bond enthalpy of 413. I have 1 carbon-oxygen bond. That's this one here, and that has a bond enthalpy of 358. I have a single oxygen-hydrogen bond, the hydroxyl group. That has a bond enthalpy of 467 kilojoules. And finally, I have 3 oxygen-oxygen double bonds, each with a bond enthalpy of 495 kilojoules. So that's the bonds broken. The sum of all of that is 4,722 kilojoules. And I can also now just go to the other side of things and look at bonds formed. And so in this case I have 2 moles of 2 carbon-oxygen double bonds. And so that is, again, it's CO2, so it's 799 kilojoules, CO2 gas. And I have 6 moles of oxygen-hydrogen bonds, and that's 467 kilojoules. And that's it for that, not as many bonds there. And so when I do the math on that, 5,998 kilojoules of energy associated with bond reformation. And so now it's just a case of bonds broken minus bonds formed, and I'm going to do that in the middle here. Bonds broken minus bonds formed. So that's delta H of reaction. 4,722 kilojoules minus 5,998 kilojoules, and that equals minus 1,276 kilojoules. So again, there's the application of Hess's law, that equation, bonds broken minus bonds formed. But all I've done here is looked at all of the bonds just in the bond breaking side of things, and centered those out and calculated a delta H for the bond breaking component. Remember, this is delta H for bonds broken. And here I have a delta H for bonds formed. And then I just do the subtraction, and you get that works just fine. Let's look at one more example. How about a substitution reaction between iodo-ethane and water? And so if that's my balanced equation for this reaction, again, I can look at a simple stick diagram. And so my stick diagram is going to look like this. Carbon with hydrogens attached, and on carbon 1 I have iodine, and the rest are hydrogens plus water. Yields. So that substitution reaction yields an alcohol, right? I'm going to substitute my hydroxyl group onto that carbon. And so I get this ethanol plus hydrogen iodide. So now I have all my bonds. And so let's just look at that same process, bonds broken. So delta H, we're going to look at delta H for bonds broken. So what I have is 1 times carbon-carbon, again in the middle of that backbone, 5 times carbon-hydrogen. I have 1 carbon-iodine bond, and I have 2 OH bonds. All right. And before I go any further, I'm going to look at bonds formed next. And what I have here is 1 carbon-carbon bond, 6 carbon-hydrogen bonds. Whoops, I don't have 6. Still have 5. 5 carbon-hydrogen bonds. You maybe see where I'm taking this. I have 1 carbon-oxygen bond. I have 1 oxygen-hydrogen bond, an hydroxyl group, and I have 1 hydrogen-iodine bond. Now, I can simplify this before I actually even worry about the math. 1 carbon-carbon bond. 1 carbon-carbon bond. Well, the enthalpy of formation minus, or sorry, the bond enthalpy minus the bond input to that is going to be 0. So I can get rid of those. 5 carbon hydrogens, well, bond enthalpy is going to be the same. 1 carbon iodine, I don't have another bond, so I'm going to need that one. 2 times oxygen hydrogen, 1 times oxygen hydrogen, well, that's actually only 1 oxygen hydrogen, so I'm going to have to do that, need that one. And I'm left with 1 times HI. So now I can just go to my table and look up these few bond dissociations. That's 240 kilojoules. And this one is 467 kilojoules. And my carbon-oxygen bond is 358 kilojoules. And my hydrogen-iodine bond is 295 kilojoules. And so now it's a lot simpler problem. Bonds broken, 467 kilojoules, minus bonds formed, which is 653 kilojoules. When I add these two together, I get 467. When I add these two together, I get 653, and that yields, whoops, so the totals here, when I add those up, the total for the bonds broken, delta H of bonds broken, is 707 kilojoules. The delta H for bonds formed is 653 kilojoules. And so delta H for the reaction, bonds broken, 707, minus bonds formed, 653, equals positive 54 kilojoules. And so I can see that this substitution reaction, the substitution of an OH group onto iodo-ethane, is actually endothermic. So if I was to give any advice, the main advice I would give when you're dealing with bond energies is you must have a good appreciation for the bonding. And that's why, in my opinion, the stick diagrams are very useful and certainly well worth the time at the start of the question, quickly drawing those out in order to get a really good handle on the number and type of bonds you're dealing with. And that concludes this video.